So I think what we're going to try and do this morning is have a bit of a chat about TCP IP networking and particularly how we use it in IoT and the Internet of Things. So I don't particularly want to kind of spend my time sort of talking at you. Yeah, that works, that's good. I haven't got one of the indelible ones. Really what I want to do is try and give you a bit of background, stuff you may know, stuff you may not know. If you do know stuff, we don't really want to focus on it. What we want to give you is a framework to be considering what's going on when you're actually programming and working with embedded devices and moving data around the internet and all those kinds of things. So that's what this is about really. So it's much more of a sort of free-form chat than anything else, and we will just sort of go wherever the wind takes us to try to answer any questions, and who knows, maybe I'll learn some stuff as well. It's entirely possible. So I suppose the first thing I might ask you is who invented the internet? What would you say? Any ideas? Any names come to mind?
This particular name, but I can't quite recall.
Okay. Have you done any modules on TCP IP on the internet? You must have, yeah? You must have done some stuff.
Undergraduate? Undergraduate or?
Yeah, well.
Yeah.
Okay. So I was talking to somebody the other day, and they said that the person who invented the internet was Tim Berners-Lee, who was one of the big names in the world of the internet. A lot of people think that, and you know, maybe they're right. People have different opinions. I have a different opinion. Tim Berners-Lee is the guy who invented the World Wide Web. The World Wide Web, WWW, is essentially this thing that we all use that we don't think about anymore, which is web pages and hyperlinks between web pages. And he came up with the idea of this hyperlink, this way of having a referenced set of information, a page of information, say, which could link to another page of information. And in that way, you could move from place to place to place within this virtual world of the internet. And so when anybody, or when most people interact with the internet and the computer systems, they tend to be thinking of web browsers and web pages and portals and the services that are offered on those portals. And that is the World Wide Web. And that's hyperlinks, and that's Tim Berners-Lee. But that is very much just the tip of a very large iceberg. Because all of that stuff sits on top of a lot of other stuff to make it work. And the basics of it all is that we're trying to move bits of data from A to B, from place to place, in a somewhat reliable kind of way. And that's what the internet is about. It's inter-network. So you've got a network, and then you've got a lot of other networks, and we move data in between those networks. And the overall set of all of these networks is our global internet. And we have smaller private networks within that overall network, and we have disconnected networks and these kinds of things. Now, where a lot of this came from in the early days, as a lot of things do, was through military research. And there was a program in America, which I think was DARPA, and they created the ARPANET. And, you know, you can go and research all this stuff, and I'm giving you a kind of my opinion version of all of this, and others may disagree. But in essence, what it was about was, you know, back in those days, which is probably the kind of, you know, the late 80s, early 90s, I guess, we were looking at how you move digital data from place to place in a way that could route around problems. So in the bad old days, when the telephone exchanges were first created, I'd have a phone in my house, and I'd ring on that phone, and there would be a physical wire that would go to an exchange place where people would work, and they'd pick up my call, and they'd physically connect my call to another place which would physically connect those bits of wire, and I could speak to the person that I was intending to speak to, and then physically disconnect that, and a different call would physically go to a different place. So you can imagine if at any point in that process those bits of wire got broke, I can't make my phone call. And then we you know, you can think of that as analog data, because that's analog data being encoded onto these bits of wire and then being decoded at the other end. So it's sort of an evolution of the telegram and Morse code and ... We're carrying audio now, but it's still analog. And then we started to move into a world of digital, where we would encode things as zeros and ones. And we could break up things into blocks of zeros and ones, or packets of zeros and ones. And then if I've got a few different wires between where I am and where I'm trying to talk to, I don't have to send everything over the same set of wires. I could send some stuff over one set of wires and other stuff over another set of wires. And then if one of those sets of wires fails, well, I can still get my information through. So this idea of the ARPANET was all about how do we really reliably move data around and manage this process of taking different routes to get that data where it needs to get, when we can't control what those routes may be, when they may be working or not working. That's where the idea comes from. So there's a lot of memes to do with all of this stuff. One of the sayings is the internet routes around, and that's used in a lot of different ways nowadays, particularly to do with information and keeping information secret or confidential. But in essence, it's the same thing. What it's saying is that if there's a bunch of wires over here and something goes wrong, the internet will magically find a way of moving that data through a different route to get you what you need done. And that's what it's all about. That's what the internet TCP/IP stack is all about, doing that. So it doesn't have to be TCP/IP. There are other protocols, other ways of doing this stuff. They've all kind of disappeared, really. Mostly, pretty much everybody who talks about the internet today is talking about some implementation of a TCP/IP stack to move packets of data around. And there are different levels and protocols within that TCP/IP stack to enable the different things that need to happen. And a lot of the time, we kind of ignore all the stuff we don't care about. And particularly as engineers, we kind of have to do that because the world is so complicated. If we investigated everything, we'd never be able to get everything done. So we just treat things as a black box, we let them work, and we get on with the bits that surface that we need to care about, which is often at an application level, where you're trying to write a bit of application code on a phone, or a bit of Python, or an embedded device to move information around, and it disappears into this mad, crazy world of this TCP/IP stack, sort of reappears somewhere else, and then you deal with it. You don't quite know what happened between these two things, but it's useful to be able to take a view on what's actually going on, particularly when you're trying to problem solve and configure things when they don't work as they should. You don't quite know why they're not working as they should. So one of the things that you probably got taught is about something called the OSI model, which seems to be what universities really like to teach. And that's a layered model to express how information moves around something like an internet. TCP is very similar to an OSI model. I can't remember it. So could you look up the OSI model, and then you will see you'll probably see a graphic, and you'll see there's a stack. And if you just tell me the different levels within the stack for the OSI model, we'll have a little bit of a chat about them.
Application layer.
So let's put that down here. I'm going to try and change the pen because this screen is not very effective. So the OSI model, up at the top, we've got the application layer, yeah.
Presentation layer.
And the presentation layer.
Session layer.
Session layer.
Transports.
Transport layer.
Network.
Network layer.
Data link.
Was it interlink?
Data link.
Data link.
Yeah. Then physical layer.
And then physical. Okay. So I'm not going to sort of try and explain all of this, except to say that each of these layers, from application up at the top, down to physical down at the bottom, sits on top of the layer beneath it. And you can think of physical down at the bottom as a bit of wire. So what's happening is, if I've got my computer A, or my device A, and I've got my computer B over here, and that's also got these layers inside it, like so. This is a logical model for a software stack. So you can think of that as, you know, a library, say, or a set of programming that's sitting inside the computer. Typically, this would be a TCP/IP implementation that sits within a kernel of an operating system that you're using. So that would be Linux or Windows or Mac or whatever it might be, iOS, yeah? And this will sit inside every device that uses this mechanism to access the internet, from your phones to your little ESP8266s. We work in that type of thing. Physical is the bit of wire. Data link is getting a packet of data from one place to another place directly. Network is getting a packet of data to a far away place, which might go through other places to get there and be routed from A to B. And then we've got transport and session and presentation that I tend not to bother with, an application up at the top, which is the specifics of what you might be doing. So you can think of that as a request from a web browser to a web server, or a request from an email client to an email server, or a request from a chat client to a chat server. And something we need to come back to a little bit later about what servers and clients actually are, but we won't worry about that just now. So if you think about what's happening on a physical layer, that is tending to be actually voltage levels changing in a bit of wire. So if you think about, you know, I know we're all using Wi-Fi today, and I'll come on to that, but step back from that because it's simpler and just think about Ethernet. So I plug in an Ethernet cable into my adapter on my computer, and I plug the other end in somewhere else, and that's the bit of wire. And there's an Ethernet PHY, an Ethernet controller, the physical access that converts ones and zeros into changing electrical pulses that go over this wire. That's all that's happening. And there are different ways of doing that in coding, but obviously for this stuff to work, there have to be standards. So there are Ethernet standards, 880 series standards, for how that data gets encoded on bits of wire. More recently, I mean, maybe not for you, but for me, that bit of wire you can think of as radio. So obviously radio communication, there are no wires, but what's happening is those zeros and ones are being encoded in radio spectrum to send that information from a point to a point. Wi-Fi is a bit different because it's broadcast, whereas Ethernet is point to point, but we can deal with that separately. So we'll keep this in the back of your head, because all I'm trying to say here is that there is a structure to how this stuff works. And in terms of how data is sent out, what you tend to find is that I've probably got, these pens are useless, I've probably got a packet of information here that I care about, which is my zeros and ones. And maybe that's the web page that I want to retrieve or something, who knows, I don't, actually it's not a good example, but. And then as we go up this stack, down this stack, headers are prefixed to the front of this packet. And those different headers relate to different aspects of this. I'm going to start calling it TCP/IP stack now, which is a more specific instance because that's what we care about. So you'll have one packet of data here relating to a level, which might have some more data outside it relating to a different level. I might not be explaining this tremendously clearly, but hopefully it will sort of begin to come together as we move forward. So let's take some examples of this. I've got a laptop here, sitting on the table over here, and I want to send a message to one of you two on your laptop B over here. So there's different ways we can accomplish this, and the first thing that we can look at is that, let's say these two laptops, again we'll leave, Wi-Fi is similar, but we'll leave Wi-Fi out of it. We're talking about wired Ethernet now, talking about wires connected things. So this computer is connected with Ethernet to the network. This computer is connected to the local network, so they can move packets of data between the two of them. Now, first thing is, how do I know to get my information to B? Well, there has to be some kind of identifier here, doesn't there? We've got to have identifiers to sort of indicate what we're trying to do, where we're trying to get the data to. And there are different kinds of identifiers. So at the lowest level, down at the bottom here, at the data link layer, we've got something called a MAC address. You heard of MAC address?
Yes.
Good. Any idea what a MAC address is?
The specific device address.
Unique ID.
Both, yeah. So I think if I remember rightly, it's a media access control address.
Okay.
And every Ethernet device that's implementing the TCP/IP stack, more or less, say, I'm simplifying, has a MAC address, and that MAC address takes the form of 6 bytes. And every MAC address is supposed to be unique globally in the world completely. If they're not unique, you run into trouble. There's an organization that you can register your MAC addresses with. I can't remember the details exactly, but I think that the front 2 or 3 bytes of data is your OUI, which is your unique organization identifier. And then the back end, it might just be the top 2 actually, and the back end is your unique device ID.
Yeah.
So typically, most people don't worry about this stuff because when you buy a laptop or a mobile phone or something like that, it's got the communications chips inside, and those communication chips have this ID burnt into them somehow, often during the production stage. And typically, if you're a smaller entity, what we would do, if we're manufacturing a board, we would buy in, say, an Ethernet controller device, and that Ethernet controller would come from a manufacturer like NXP or Marvell or whatever it might be, and that manufacturer would already have bought a block of these MAC addresses, and it would already have the programming in. So if you look at MAC addresses of devices, and you can run, something like ifconfig on your laptop there, and it will give you a unique MAC address for every adapter interface that you have in the system. And you can look up that MAC address on, there's various different resources, there are online resources to do MAC address checking, and it will tell you what the manufacturer is for your MAC address, and that will generally be whichever company sold the silicon that is supporting that function, like the Ethernet or the Wi-Fi, whatever it might be. So that's how that stuff is structured. Now, this looks a bit like an IPv6 address because they're the same number of bytes, but it's not. It's a different thing for a different purpose. And so what you can do is you can say, okay, well, I have a packet of data over here, and I want to send it to this MAC address over here, and then we can let the bottom layers of the stack work out how to do that. And then we can send out the information over, for example, the Ethernet adapter, and then anything else that has that MAC address says, oh, look, that's for me, that's okay, I'm going to deal with that packet. There's a bit more to it. You can also broadcast information to all devices, which would be all Fs in your MAC address. And there's something else called multicast that we won't worry about. But basically with MAC addresses, you're talking from one computer directly or device directly to another computer or device on the same network. And that's critical. So if I've got another network over here with some more computers on that network, C and D, and they have their MAC addresses, I don't have any way using MAC addresses at this data link layer of getting my packet of data from A to C. Doesn't do it. That's why we need something else. We need the networking layer. Now, before we start to talk about that, this is where we begin to bring in the concept of IP addresses or Internet Protocol addresses. So we talked about MAC addresses, these things, and now we're going to talk about IP addresses. And when IP was created, it was IP with 4 bytes of address, and so we now call that IPv4 to distinguish it from the newer IPv6. I'm not sure if we'll get on to talking about that. What time is it now?
Around
Drop
37.
37?
Yeah.
Can you just keep an eye and give me a shout at about 5:02, and I've got a hard stop then, and then we'll kind of resume after the meeting I've got. So an IPv4 address, again, that's a dot notation usually, so actually that's unhelpful. So let's just say a typical IP address that you will know and love is 192.168.1.1. And in internet parlance, we call these octets. And that's a pedantic way of framing it, but it's because a byte doesn't actually have to be 8 bits. Anytime anybody talks to you about bytes, they will mean 8 bits. It doesn't actually have to be 8 bits, back in the mists of time. Whereas an octet is 8 bits. And these things are 8 bits. So you've got 1, 8, 16, 32, so it's 32 bits long, and that gives an identifier, an address for some kind of device. And those, as you know, don't necessarily have to be unique. You know, I can go home and I might be talking to that IP address, which might be my gateway at home, and I might come in here to DOS, and there'll be a completely different system. So these are mapped all over the place. Now, the way IP addresses, in the same way that I told you that the MAC address space is broken down into an organizational block and unique IDs within that organizational block, IP addresses are broken down into classes A and B and C. And there are 3 relevant things here that you need to understand and consider when you're thinking about dealing with IP addresses and configuring IP addresses. One is you've got this IP address thing here itself, which is kind of what you're mainly looking at. You've also got something called the netmask, and you've got something called a network, and then you've generally in here as well got a gateway. And I'm going to try and talk about why those 3 things are important for your thinking. So, classes of IP addresses, there's a reason that these things are broken down in the way that they're broken down, and it's to do with a network as opposed to other networks, and how many devices you have on a network. Now, a Class C device is defined by a netmask of, I shall try and put it in here, 255.255.255.0. I'll explain what that is in a sec. Class B is 255.255.0.0, and Class A is 255.0.0.0. All seems a bit random, doesn't it? You'll have seen it, you might well be going, yeah, I don't know about that, but I never really understood what the point of all this stuff was. That can be represented in a different way. Sometimes after the IP address, it's represented as a slash followed by a number. And in this case, it would be an 8, a 16, or a 24. Those are the class of the networks. So Class A has, think of the 255 as ones. So it's all ones in the first octet, and then all zeros, which is 8 ones, which is /8. 255, 255, 16 ones and zeros, 16, 255, 24. There's actually numbers in between these, and some people do. If you're a network admin and you're doing this stuff, there are reasons you might not use these sort of standard numbers, but that's what most people use, in my experience. And the reason for this is that the class and the netmask in the front bit, if you like, defines actually, let me put it a different way. The zeros that you have at the end define how many devices you can put, you're a network admin now, how many devices you can put on your network. That's because each device has to be unique at any point in time. I'll go back and say MAC addresses are always unique all the time, everywhere. IP addresses, you can set them up or you can assign them, we will talk about that. But at any given time, within a network, IP addresses have to be unique, but they can change, as we know. We have problems with that sometimes. So, typically, what you see in the home, and actually Netting does, I think we're a Class B, but typically in the home, you will have a Class C network set up by default. And that's because a Class C network can have up to 8 bits worth of numbers, devices on it, which is 255, 0 to 255, or 256 unique combinations. 0 and 255 are used for their own purposes, I think. Don't think 0 is used. 255 is certainly used for broadcasts. So you're limited in the number of devices that you can have, but it's more or less 253 devices that you can connect up in your home to your access point. That's your network. And nobody really thinks about it. It's not really a problem because, you know, you're going to have a couple of hundred devices floating around, not really. You know, 5-10 years ago, you had 1 or 2 maybe. Now, IoT in the smart home, you've got quite a lot more. You might have light bulbs. You might have 20, 30, 50 maybe, some people. You're still not really up to a couple of hundred. That might change in the future. I'm not sure. Don't think so. So we don't really worry about it. We have Class C networks in our homes, but you can see that if you're in a business, I mean, even in DOS here, you could quite easily end up with more than a couple of hundred, 250 odd devices. And then what do you do? You got a problem now. So what you do is you go to a different class. You go to a Class B network. Class B network, and you've got 2 octets to play with here. And you know your binary, you know your 2 to the power, so that's something like 16,000 odd different devices. Now, that should be enough for your business, you would think. And then, and that's a somewhat unlikely scenario, I think, but say you're a big multinational business with stuff all over the place and you have everything connected up to everything else, which of course you don't for security reasons, but you could see that you would have lots and lots and lots and lots of devices, and you've got a Class A network for that. Now the key thing here as well is that, and a lot of this goes back to history again, because, you know, if you're dealing with laptops today with 8 gig, 16 gig, 32 gig of RAM, multi-cores, loads of storage, you know, it all seems, you know, endless and free. But when all this was coming about, and when I started out, we were really worried about trying to shove all the information that we needed to shove into the very limited amount of memory that we had, because it was very expensive. So a very great deal of thought went into optimal use of all the bytes that you've got available to you in your RAM. So what you can see here is we've said we've got a 32-bit value for our IP addresses, and we split it up in different classes, and we say, you know, we've got more or less devices in different classes. And you can see that on the other side of it, if I've got a Class C type network, I can have quite a lot of networks with not very many devices on, because I can have, you know, whatever that works out to be. Class B network, I can have 16,000 odd networks with 16,000 odd devices. And a Class A network, I'm very limited. Globally, I can only have about 253 networks, but I can have lots of devices on them.
So I have
Yeah,
a question.
jump in.
Can we have multiple class in same network? Like in DOS we have class B and class C. Is it possible?
That's a a very interesting question. The simple answer is no. I'd have to think about that. It may be possible to... No. The answer is no. I'll come on. I may be wrong about that answer, so investigate that and pick me up if I am wrong. But I'll come on to try to explain why. Okay? It should become a bit clearer. What time are we on now?
47.
47, a little bit longer then. Okay, so
So we can't use 225, 225, 225, 1 or 2. So if I'm using class B, I can't use IP address 225, 225, 225 B.
Because class C is actually part of class B, so you can't have them both.
very good point. So I'll try and answer that in a second, but this is what I was going to say. So what you're identifying is correct. This couldn't work if it was just that simple, and it's of course never that simple. So what you've actually got is, what you will see is that a class C network is prefixed with 192. Usually 192.168 actually, I think. A class A network is prefixed generally with, I think, 10. I can't remember what the one in the middle is. If you look at an IP address, because of the way it's specified, you can generally tell what kind of class of IP address it is. Now that's not a mathematical absolute, that's what the standard says. So in DOES, if I was a network admin, I could set up computers to have addresses of a class C network, and I would tend to use 192.168.something.0.1. And that's why you see that everywhere. Now there's nothing stopping me setting up a network which is a class C network beginning with 10. I can do that, but it's very bad practice because people look at a 10 and they don't expect it to be a class C network. And effectively, that 10 actually might be a class B. Can you just look up what the IP address prefix, the network prefixes are for classes of IP networks, so we get this right? Can you see anything?
So they are saying 1 to 126 is for class A. 128 to 191 is for class B. And 192 to 223 is for class C.
There you go. So 192 is the start of the class C networking space. And so that's what you should be doing in terms of how you begin your networks when you set up a network somewhere. And so you can take a quick look at an IP address, get a pretty good idea what kind of network it's sitting on. Now, logically, what's actually happening in the silicon, in the hardware, is that you've got this netmask and that netmask is being applied to your IP address, which is going this way, and what it's doing is it's giving you, it's a logical operation, so an ANDing or an ORing, and those ones and zeros we looked at in your netmask are being ANDed in, say, to split out the network bit, which is the bit at the front of my IP address, from the device bit of my IP address. So as these IP addresses are flowing around, every computer, every adapter that's dealing with packets, if you run ifconfig again or ifconfig again, you will see that your adapter has its IP address and it has its netmask. It's the netmask that defines what the device is and what the network is.
Okay.
So you can assume certain sets of things because they're standards, but what you actually do is you look at your netmask, which will almost always be a class C network with what you're dealing with, and you say, that's a 24-bit, that's a class C network, that means my network is the first 3 bytes, 192.168.1, whatever, and my device is the last byte. And what you find if you look at your IP addresses now, if you read out your IP address,
172.17.0.1.
doesn't sound, is that right? What's the adapter for that?
Docker.
Yeah, so that's different. That's an internal IP address. That's kind of like a virtual IP address that we'll talk about separately maybe. You want to look at your Wi-Fi, your WLAN or your W.
So it's 10.0.34.120.
10.0.34.120.
Yeah.
And what are you on?
Let me just check on Windows.
Sure.
By the way, your time is.
Okay, we'll go. But basically, I think what we're going to, and what's your netmask it's showing you?
Sorry. 255.0.0.
255.0.0.0. So it's a class A,
Yeah.
beginning with 10, which is this thing here, and that gives you loads of devices, because the guys who set the network up here, and I say guys because they're guys, clearly decided that they wanted a class A network with lots and lots of devices on it.
Yeah, I've checked mine as well.
Yeah, and what have you got?
10.0.29.1.
29.1. So you can see, and it's a good example, that you've got 34.120 and you've got 29.1, was it?
Yeah.
But you're on a class A network.
Yeah.
So you're still within the same device space,
Yeah.
and you can still talk to each other.
Yeah.
Now, if you were on a class C network, that would mean for you to be able to talk to each other, all 3 of those network octets have to be the same.
Oh.
So if you're trying to debug problems with connectivity, one of the aside from checking things are plugged in, one of the first things you're trying to do here is to look at what is my network configuration, what is my netmask, what network am I on, and am I on the same network as what I'm directly trying to talk to. This is particularly when you've got a laptop and you're debugging embedded devices, they're all connected together, you're trying to get some life out of it, you're not sure why not. First thing you're doing is checking that the network octets, which will be 1 or 2 or 3 depending on the class, are right and the same, or you won't be able to talk to each other. And we'll come on in the next session to explain why that is and how the internet works with that. Okay?
Yeah.
You still awake?
Yeah.
Yeah.
Good?
Yeah.
Useful?
Yeah. Very.
Hope so.